Okay, good afternoon, everyone. Thanks for joining us for today's Geographical Water Security Alliance seminar. So today we are having this in hybrid format, and we have Courage Zabian coming back to Exeter. He was working with us a couple of years ago, and it's very nice to see his got very successful career in University of West London and coming back to us to share what he's been doing in the recent years. And also I'm very happy we have a lot of interest for the people online joining us today. So we'll put a very good ending for this academic year's webinar. And can I just remind colleagues in this room, we use this because the hybrid, so the microphone is very sensitive, so it may pick up your voice, so it might distract people a little bit. So please be aware of this situation. But with no ado, I would like to introduce to give the floor to Professor Courage to give the talk. Thank you.
Thank you very much, Albert. I'm just very happy to just be here and to give you these presentations. This presentation is about a data-driven modeling approach that we're just going to follow for flood forecasting in urban drainage systems. And this is like the part of the works of my PhD students that we just been working over the last couple of years. My PhD, his name is Farzad, and he actually has done a lot of work in this area. So the outline of the work that I'm just going to do today, I'm just going to introduce the research team that I've just been working with. First of all, we're just going to start with the challenges and drivers that we have, and then key features of the data-driven models. And then I'm just going to introduce the case study, and then results and analysis and discussion. Okay, first of all, the research teams. Once I'm just going to move to University of West London, I've been working with a large number of people, interdisciplinary area, and in different research groups. I've just been working with the 3 research groups and 1 research center. And these are some of the colleagues that we just have at University of West London. Also, I've just been working with some external academics in the UK, specifically in the Center for Water Systems, and also in UCL and other UK universities, and also other universities in the international. I've just been working with some industrial partners, SME, and also water companies, and some councils as well. I'm just going to go through with the start with the challenges that we have. As you may just know or familiar with some of these challenges. The first challenge that we have is the population growth. As you know, the population is going to increase more and more, and as a result of that, the urban population increase much more, especially just going to increase 50% by 2050, specifically more in Asia and Africa. And with that the increase in population, we have an increased demand for water, energy, and food, and also safe water. We have a problem with 21% of the population in the world. They don't have access to safe water. The other problems that we have, climate change. Climate change has got a major negative impact for water scarcity, and also for the flood. During the last 40 years or 20 years, we have more than 2 billion people have been affected by the flood. And the climate change can cause the flood and droughts is going to happen more and more frequent and more severe. The other problem is aging infrastructures that we have. Because of the huge capital investment, the governing body or the government, they don't have enough budget to just rehabilitate the whole infrastructure in the water, specifically in the urban water systems. So if we have some bibliometric analysis of the studies in the recent 30 years about the occurrence of the flood events all over the world. As you can see here, the number of flood events in the studies that we just seen, a lot of the cases happens in Asia, China, India. I might just bear in mind, this is with the caveat of the name of the country or the size of the country that may not be show the true picture of the whole in the world. But specifically, you can see in the east of Asia, number of flood events has been much higher compared to the other parts of the world. And in terms of the average human loss, you can see here north of Latin America, and also again, like in Asia, you can have like the highest number of the average human loss as well. If you look at the affected people again, like the people more in like the Asia is south and east of Asia, we can have like a more number of people affected, and also affected average economic loss as well, like you can see in North America, and also like again in Asia, and also like in Europe as well. This is like the average economic loss that we can see here. If you try to just see the impact of the climate change as well, if you can just look at the frequency of the floods all over the recent 50 years, you can see there's a linear trend of increasing trends of the frequency of the floods that you can see is increasing, and that's a result of the climate change. And the same, you can see some exponential increase for the affected population and also economic loss as well. And you can see like the distribution in the world as well, how it is going to change. And at the same time, we just have like the challenges. We have some promises by water companies, specifically the water companies. The water companies in the UK, they promised they want to just have more challenge, and they decide to just go with the net zero emissions by 2030 instead of like a 2050, which is like a really challenging. And that can just save a lot of like the emissions, around like the 10 million tons of greenhouse gas can be saved within this period. But as you know, what's like a part of like the urban drainage system that is more like the water intensive for energy is like the transportation and the treating water is the energy intensive part, and which can create and result in a large amount of the greenhouse gas emission. And the solution, as you know, is not like a single solution for that, and we need to just look at the combination of approaches and collaborations between all like the stakeholders, including water company and communities, policymakers, and other like the relevant like the people involved. And at the same time, you know, due to the like the advancements of like the technologies that we have a lot of like the new technologies, like for example, rainwater harvesting, greywater recycling, or any kind of like a water recycling. A smart like the technologies we can just optimize and provide like a better and more efficient like the system operation. This is like a really promising technology that we can use. At the same time, we have the United Nations Sustainable Development Goals. As you know, like there are like the 17 like the goals. And I can see, you know, like a good number of them are either directly or indirectly relevant to the water. We're just going to see, for example, even zero hunger, because of the water, it has got a nexus to the energy and food, is indirectly relevant to the water. Some other like a good health, waterborne disease as a result of the flood. If you want to just manage the flood, we can just have an impact on this kind of like the number 3. And clean water is the same, number 6. Affordable clean energy is also like that because of the nexus of the water energy. We are have an impact on that as well. Infrastructure, the same, that once we have infrastructure. And sustainable city, again, for urban drainage system, we can have an impact. Sustainable productions, again, for the water, energy and food, the connection with the food nexus, it is the same. Climate change, life below water, because of like the pollutions, we can have like an impact on the like the water, and also like we can see like a partnership as well, and even peace. You know, we have like a lot of war because of the water as well. This can have like an impact on that system. So the challenges that we have for applying or like applying for all of these technology with regards to this sustainable development is because of the capital and large capital investments, as we said, for like a rehabilitation or like a using or applying all of these like the new technologies. But the other like the challenge that we have, as you know, like the challenges of the water and energy nexus, we can see here, we have like the either technology we can categorize as either like the efficient or intensive. Some technology are very water efficient, but they are very energy intensive. For example, desalination system, other things. Some other like the technologies are both intensive from water and energy, some the other side. So we try to just approach the idea in here. In fact, we have some other challenges as well. So could be like the adoptions, could be like a cost as well. So sustainability aspects has to just be considered all of these cases here. And the other problem is that from like the cultural, technical, and financial like the aspects, they might just we have like some difficulty to just convince the people and justify to just use these kind of like the things. We just talk about like the sustainable development. Let's just look at the concept of the sustainable development in urban drainage system. As you know, we have like the two aspects of the approaches to use the sustainable approach, development approach, either like a hard engineering approach, that's we can just use the new pipeline or conventional like the new like the development extensions to just move the flood as soon as possible to the like the downstream to the like the water bodies. Receiving water bodies could be like the rivers, lakes, which is only like the in flood, which is not like the sustainable. The other approach that we're just going to use is a soft engineering, which is like the more appropriate and more like a new and modern. We try to just minimize and control the surface runoff from the source by using interception, infiltration, evaporation, and any kind of like the techniques that we're just going to do. And as you know, like the sustainable drainage system is a popular like the themes for that. So the thing is that, and one of the like the regulations specifically in the UK is that any new development is not supposed to just have contribution to the flood risk as well. So as size or anywhere else. And all of this soft technology, we can also like equip it with some like some sort of like the flood forecasting system or early warning system that can be like improve the efficiency of these systems. So we just talk about like the flood risk. Let's just very quickly look at the like the flood risk and alleviations. As you know, we're just going to define the fluvial floods once we have like the rivers like the spill onto the like the floodplain. And we can just define the flood risk normally as like the multiplications of the probability by the consequence. So the probability we can say is the frequency of the occurrence, and the constant is like the flood impact. And how we can just alleviate the like the risk, we can either like the reduce the probability rate, or by, for example, raising the flood banks, we can just reduce the frequency of the like the flood from the bank, or we can reduce the consequence. The consequence, we have like a list of like the measures. Some measures that we can just use is just to provide like the flood warning systems, alteration to houses to be more resilient or resistant, channel improvement, permanent flood embankments, and also like a flood relief or bypass channels. And you can see here, for example, a channel improvement or bypass channel here exactly. I think it's like from these pictures from Exeter exactly. So so any kind of like the things we can just apply, but all of this has got like an offline and online storage tanks as well, or like a reservoir. But all of them has got like a different like a level of cost. But one of the like good things is that like a flood warning system, which is not as expensive as the other options, but we can just apply this one in addition to like a combination of other like the techniques and measures. If you just look at the like the urban drainage systems and the flood in that area, we can just have some classifications between the flood in urban areas and non-urban areas. There are some like key differences, and it's good to understand the key concepts between them. For the descriptions is that the description of the flood overflow of the urban drainage infrastructure due to the lack of proper drainage in an urban area. We can define like the flood in urban area. But in non-urban area, we can say overflow of the water rise bodies that such as rivers, streams, we can define that one. Flood causality, it could be like the mainly fast surface runoff generated by rainfall, but in the non-urban area, it could be because of, the high intensity of the rainfall. And also the duration of the flood in the urban area could be a few minutes up to like a few days or a couple of days. but normally non-urban area, a part of the day to a week. Special flood impacts could be like a small area, a street or neighborhood, but in the non-urban is like a larger scale. Special restrictions, we don't have a lot of flexibility to just do some measurements or measures. However, in non-urban area, we have a lot of like the flexibility in non-urban areas. And also the type of the impact in urban, we have like the economic, human, mental, social problems, and also urban infrastructure can be affected or damaged. However, in non-urban area, the impact is like the soil erosion, waste of the crops, and loss of the livestock, natural habitats, and water pollutions, and other like the things might happen. So it's good to just see like the difference between these two. As a summary, the key challenges that we have: limited capacity of the flow for conveyance, and combined sewer overflow, especially in the urban area that we have, aging infrastructure, climate change, and lack of the early warning systems. So specifically, we're just trying to just focus on early warning system in this kind of like the model that we're just gonna go, and we try to just provide some more like efficient flood forecasting system. So let's just look at, with that introduction, look at the key features of the data-driven modelings that we have for flood forecasting in urban drainage system. So we had some bibliometric analysis of the type of the research studies in this area over the last 10 years, or like 10, 15 years. And we did this kind of like the findings. So first of all, based on the keywords of the study that we had, we can just classify the type of the works in the recent 10, 15 years in 3 categories of the data. Some of the works are relevant to the data source improvement, like for example, the type of the data that we're just going to discuss later. And also some areas working a lot on the model development. And the other the type of the work, they're just going to work to improve or provide a longer lead time prediction. From the time frame, or all over the since 2010, you can see here at the beginning, it was mainly for using the radar systems at the beginning, and then later just moved to the model developments, and then later to just the impact of the flood. So, or the new models actually is going to be introduced later on. And if you just look at the a study that has been done all over the recent 10 years based on the review papers that we're just gonna analyze, we had most of the study has been done were done in Europe, actually 66%, and 25% has been done in Asia, mainly in China, and part of that in in North America, South America as well, and also in Australia. So let's just look at all elements of the modeling of the flood forecasting modeling in urban drainage system. If you want to just work on that, we have we need to just look at the 3 main aspects of the modeling. First of all is the data collection and preparation. We have the different sources of the data collection. It could be radar satellite, it could be a rainfall a radar station, or rain gauge station. We're just going to analyze this further a bit more later. And also once we just going to model the system, we have a number of parameters as well. And before going to do that, first of all, we need to just prepare the data. And for preparing the data, sometimes we have missing data. We need to just prepare the missing data. Or data imputations, or the data cleaning as well. So you're just going to explain this in more details later. And also we just need to look at the structure of the model, that we might just have different type of the model that we just try to just look at that. And also spatial resolution, it could be a lump, semi-distributed, or fully distributed. And finally, we need to just see what kind of an indicator we just be using for performance assessment.
That reshapes the portrait, that feeds back into the and then also that the transport.
Yeah, okay. So I think this is
some
the background
from the
Okay. So if you just look at the data collection and preparation, we have 3 main sources of the data. data may come from like the either rain gauge, rainfall radar, and weather station. We just gonna like analyze and compare all of these like the three sources together, and like the definitions of each of them. So like for example, rain gauge stations that we have like a meteorological station, like especially in the UK, it's just managed by Environment Agency or Meteorological Office or Met Office has got like a lot of like these stations. Radar station again, Met Office is responsible for that, and also we're just gonna use the radar satellite informations as well for the information that we need, specifically for the rainfall and the water levels. There are some strengths, specifically the strength of the rain gauges that they are very accurate at the points that we just collect. However, for the rainfall radar and the satellite, they are not, the accuracy is the question. For the like is good for the strength is that we can just have like a large area of the like and distribution for spatial and temporal coverage is really good, especially for the satellite. If you just look at the weakness of the rain gauge is that inability to characterize the spatial distribution of the rainfall is like a weakness of the rain gauge. And for the radar data, we have like a fail to satisfy the accuracy of the resolution requirements as well, and the same for weather satellites for the inability to provide the high resolution data. So that's like something that we have. And also like the calibration, high systematic and calibration error that we might just have for the rain gauge, specifically once we have like a strong wind, evaporation, or a splash or other things. And also we might just have the same for the rain radar. If you have like the shadowing, weather shadowing, or like the terrain barriers between the radars, we might just have like an inaccuracy. So the thing is that the best approach might be is just to integrate all of these approaches together or merge the different types of the approaches. Specifically with the rain gauge and radar data, we can see there are some studies that try to just look at this. Majority of like the method, they're just going to use the interpolation approach, and the kriging is like a very popular for the like the interpolation approach. Bias adjustment is another like approach that they just have like some specific method they're just going to use. And the idea behind this merging is to just take advantage from the strengths, and we try to just minimize or remove the weakness of each of these approaches. So let's just look at the modeling of urban drainage system. If you have like urban drainage system, we can have like a different types of modeling. First of all, we can just use experimentally based modeling, for example, in the lab, or we can use the physically based modeling. For example, the SWIM software is a very popular one. But as you know, like for example, physically based modeling is a data demanding. We need to just provide or have access to a lot of like the data, all the pipe diameters, like the channels or the conduit levels, everything. We just need to just have that one. Researchers, they try to just come up with like a conceptual based model. The level of accuracy is not as accurate as the data physically based models, but we can just prepare and make the model much quicker and might be good for the planning purposes specifically. The last time is like a data-driven based model or empirical like the modeling. We're just gonna try to just use the data of like, for example, the source of the rainfall. And also we just look at the like the flow or like the water levels, and we try to just use some sort of like the data-driven model, could be like the machine learning, artificial intelligence, and we try to just optimize the algorithm that we have, and we can just try to just predict or the flood in the system or drainage system. So today we're just going to try to just focus on this more importantly, but before going to do that, we had some analysis between these models over the like these 10 years, like the studies in the literature. So as you can see, majority of like the model, they're just going to use the physically based models, and also like the empirical or the data-driven models have been used much more compared to the others. Hybrid models also have been used as well. And if you look at the like the spatial resolution, we can say more or less all of these models has been relatively equal, like the percentage we can have. However, data-driven models mainly like to apply for the lump spatial resolution. So majority of these are relevant to the data-driven models, and the physically based models are more relevant to the distribution options or distribution models. So that's because of like the nature of the modeling. It is a data-driven distribution models, and we can just use data from the physically based models. And if you just look at the different types of the physically based models, we can see a large number of them. They're just going to use the swim and also the MIC and the SWM. And for the empirical or data-driven models, where we just going to have majority can just be both ANN and the curve number method, so based on the study that we have. And sometimes the neural network model is used mostly for enhancements of the physically based models as well, as like the more enhancement and better like the predictions. And we can see here only 20% of the study, of the 37 studies that we just collected, they use the AI for urban drainage systems. Okay, so with that, let's just look at quickly to the schematic representation of the rainfall runoff. We assume 4 states we just have for the rainfall runoff. Once we have like the rainfall, there is no runoff. So there is no change. This is like the change of the runoff, and this is the rainfall, the top one. So S1, there is no rainfall, no runoff. Second state is that we have no rainfall, but we have a runoff or change of water rise. Okay, that might be because of the sewage diurnal, like a sewage system. And the third one, we have the rainfall, so the wet weather, but there is no like a change of the runoff, is because of the like evaporation infiltrations. And the fourth one that we are interested is that we have a rainfall in the time series, and we have also runoff as well, unchanged in the like runoff. So you can see the capacity here. So we might just have overflow as well. So this is something that we try to just predict, like this study. And specifically, but the thing is that we need to just select and detect all of these events that we have based on the time series of the data that we have. So this is something that we try to just analyze in our model. So the events of the flood or the events of the rainfall that we can have a lot of the change of the runoff, we try to just identify and try to just train our the model based on those only events, not the whole the entire data. So before going to do that, for the imputation method, we just look at all the available imputation the techniques, and we try to just come up with this algorithm that has a combination of a few traditional methods, linear regression, non-linear infilling, and T-cupola infilling, and also moving average infilling by using the benchmark data. So this is the algorithm that we just prepare. So we just kind of to show some of the results based on the algorithm that we have here. So I'm just going to do very quickly to the go to the case study and show how we can develop the model. Okay, so the case study that we're just going to analyze here is a part of the northwest of London in Hillingdon area. So this, you can see the whole catchments here. This is not the whole catchment, it's not like the urban area. Most of it is like a non-urban area. So you're just going to pick up only this wide small catchments. It's like a 13 square kilometers. And we had here the dark blue is the Riselip gauging station. We just had access to the Riselip gauging stations online. And we had because of the dominant the wind direction, we just looked at the rainfall station at the south of this kind of the gauging station. And we had a 3 station. One is the Heathrow. This is the Heathrow rainfall station. The second one is the Iverheath. And the third one is the RAF, Norfolk rainfall. So we just use all of these 3 stations. We had access to all of these information as well. And we try to just analyze and see the correlation with this kind of station. First of all, we just trying to just see the variations. You can see here, this is a water depth or water level. You can see the variation of the water level. We had the data for around I think 13 years from 2009 until 2000 and now. And this is the rainfall. The light blue is the rainfall, and the bottom is the water level. And every 15 minutes, we had the timer. So first of all, we just did some cross-correlation analysis to see what's the correlation between the each of these rainfall station with this kind of like a rain gauge station, Rice rain gauge station. And with each of them, you can see the correlation here and with the lag time. As you can see here, the maximum cross correlation is going to happen with the RIF north node. RIF is here, is number 3. Number 3 is the highest one, is like a 0.3. It's not like a very huge, but it's still something that we can rely on that compared to the other 2 stations. We can use all 3 stations together, but you know, we try to just, for this like the test, we try to just pick up only the best one or the highest correlated one. And as you can see here, all of them has got a like a lag time. That meaning that means that, for example, with that lag time, like for example, up to like a 15 minutes is like 3 hours. Maximum 3 hours, we can have like a maximum lag time. So we're just gonna like look at here. So we just kind of like pick up the RF north node station and just use this one for our like analysis. So the data we're just gonna use, we just use the DEFRA is like a free available like data, and there is a like the API, everyone can have access to that. And for historic one, you can email them and they can send it to you straight away. But for like the online one, is there's a like the API code, and you can using by your like the code, you can access to them quickly. So this is like what we just have, and for these kind of like the stations that we have, for both rainfall and rain gauge and water level, we have like a 13 years like the data we could use. As I said, the hypothesis behind this kind of like the method that we developed was that we try to just conventional like the model, they try to use the whole data sets, the whole like, let's say like 13 years. For any kind of like a data driven, we just split the data to the like the training, validation and test, like the 70% training at 15-15. But the idea is that normally many works, they just try to just use the whole like the 17% of the data. But yeah, in this work, we try to just like only like select the event-based data all over the like the training period, and we train the model or the like the data-driven model only based on that kind of like the event-based period, which is like much smaller than like the, let's say like the 10 years. So this is like the approach for that. But before that, we need to just identify the events and create the event-based data set. And then later, we just kind of compare the conventional with the event-based like the model and see the performance of the model. So we had like 4 stages for that. So first of all, we identify the flood events in the first step. And then once we just gonna like pick up the like the each event, we need to just pick up some or like generate some earlier step and some late time steps. So how many steps earlier or how many steps later we're just gonna add? This is something that we just come up with the first of all, we're just gonna like make the cross correlation and see the maximum cross correlation, the time lag, that's C. In addition to the like the time step we use for prediction, for example, like 1 to up to like a 12, we're just gonna use here and we just add it here for each event. And then later for the later step 3, for adding the later steps, we're just gonna do the same. So we're just gonna add the same like the time step ahead, we're just gonna add it here. And then later at the stage 4, we're just gonna calculate for the new time step data set, we're just gonna see the maximum cross correlation with C star. If C star and C is the same, we're just gonna finish. If not, we're just gonna again like repeat the process with the new C star. As long as they're just gonna converge together, and we said like this kind of like the data sets is okay. So this kind of like the parameter C is iteratively changed as long as we can converge to like the fixed value. So this is like the approach that we're just gonna do. So the model, because it's a time series model, we're just gonna use the NARX model. It's very popular. For any kind of like the time series, we have to use that one. So this is like a structure that we're just going to use and code in MATLAB. So the input data, as I said, is like only one rainfall. You know, the X is like the rainfall depth that we're just going to use, and Y is like the water level as well. So the water level for data station and for both rainfall and water depth, we're just going to use a number of time steps beforehand. So the number of time steps before that, we're just going to use this one based on the maximum like a period that has got a like the highest correlation. So we're just going to use these two, and also for the prediction is based on a number of time steps ahead. Could be between 1 to 12. We just analyze all of them to see the performance of the model. So just like the model is like a more or less like a straightforward, and there's a lot of like a research, and more or less they're just gonna do the same like a procedure. Okay, and I'm just gonna like move to the like the results and analysis. So first of all, we're just gonna like analyze the imputation like the algorithm that we developed. It's like some sort of like a combined approach. As you can see, the proposed approach for non-events, non-flood events, and also for flood events, the accuracy of the RMSE of the performance of the model compared to the other models are much, much better. I mean, these are like the imputations for infilling temporal data. So you can see, like, for example, our performance is better than other like methods like the Kriging and cupola-based like the models. They might just be really good actually for spatial resolution as well, or like which is very popular. But our model is also like some sort of like improve or combined model. And as you can see here, for both like the flood event, non-flood events, for both rainfall and water level, for the missing data, our performance are better. But for non-flood events, the performance are more or less the same, because most of the time we don't have any kind of like the predictions like more or less straightforward for that. And to just show you like a slide about how it's just gonna work, to just show the performance of the model, we just intentionally remove some of the data. We knew that data, we removed that, and we try to just predict or like try to infill the data by using imputation method that we have, and see with the real data how it works. As you can see here, we just try to just use it with a high range, high like the rainfall, medium and low range. We try to just analyze that. And you can see here, the blue one is like the observations, and the proposed one is the green one. Is like the green one can track much better than the other like the methods. And the same, this is for like the rainfall data, and the same for water level as well. So we try to just remove some data from here, from the upside and downside as well, and try to just see how's the performance of model for those like areas. As you can see here, the performance is like quite satisfactory for both like the increasing and decreasing. But for this one now, most of the model can just predict very well. But for here, our models, because of like the approach, can just have like a good performance. So okay, so this is like the data preparation. So just let's move on to the main part of the analysis that we just did for the prediction. Okay, so just like I've got like a few slides to just show the performance of the model here. So the first one is like the RMSE. We have like a few indicators to just analyze. RMSE, the blue one is the performance of the conventional model. Conventional means the whole data set, and for training and for the test. For the test, we're just gonna have the same data set for the test for both like the models. As you can see here, RMSE is supposed ideally 0. So for first time a step ahead for 15 minutes, the performance, the error for both models are like quite low. But then later the difference becomes like the larger between the like conventional model and our model. So as our RMSE, and for 8 time steps, for 4 time steps like a 1 hour predictions, 8 time steps 2 hours, and 12 time steps 3 hours ahead. We're just gonna have predictions. So you can see here like the performance is like we can say like the 50% here is like much better. And again, for Nash, normalized Nash soft-cliffs error, again, the ideal value is like the 1. So we're just gonna get to the 1. So again, for 15 minutes, more or less both models are the same. And for again, for 1 hour prediction, again, our like the model has got like a 0.92%. However, like the conventional dropped to like a 0.75. And down to like the 12 times, so 3 hours ahead for predictions. Again, our model has got like a much better like the performance compared to the like the conventional one. And also for training and the test time, this is all more or less like the obvious, because like the conventional models trying to just work with like a much larger data. So obviously is for, you can see here for the event-based, which is a green one, the dark green and light green, our models work with like a smaller data set. So obviously the time you can see here for both for training and for like a test is definitely much, much lower than the one, which is actually important once we just kind of like to work with like a real-time prediction. Even for like a few minutes or like a few seconds, there's a huge difference. So we try to just have like for a few hours prediction, try to just have a model in hand that can have like a much better. for all of the models, you can see for like the different time step, either from 15 minutes to 12, like the to 3 hours, is our model performance is like quite better than the other one, which is obvious, but it's very important for us as well. Another like the parameter here is like the accuracy of the overflow detection. One of the key things here, we just try to just predict or forecast the water level. But one important thing is that to predict once we have like the overflow, once we just increase or increase the capacity of the system, or we're just going to have like the overflow. And you can see here, one thing very interesting is that the predictions of or detection of the overflow drops significantly with the conventional models and is not able to provide like the acceptable like the level of the prediction. You can see here the accuracy is quite low, however, so the ideal is like 100%. Our model is able to just predict almost like a 50% for overflow detection, which is like a much better for 3 hours prediction, which is really important. If you are able to just predict 3 hours ahead, if the overhead is going to happen for like any kind of like the conduits or the channels that we have. Okay, so we got like a few more comparison. So here is like a comparison between the observations and the predictions. You can see here left figures or left graphs related to conventional models for different time steps. You can see first row is a 1 time step, 15 minutes. Second row is a 1 hour or 4 time steps. And our model results is on the right-hand side. As you can see here, for the 1 time step or 15 minutes or like the 1 hour, the performance of the even conventional model is like quite good as well. It's not bad, but you can see the huge difference, or like the difference between blue and orange ones. The blue one is a measured and the orange is like the predictions. As you can see, like for like the 2 hours and 3 hours, specifically conventional models fail to predict the water depth or spikes. And normally you can see like more or less underestimate, but we have another analysis to just show exactly why you're just gonna have like the underestimate. But you can see here for our model can have like a better performance. Another like the analysis that we did like the analysis between comparison spread of the like this or scatter of the like the measurement and observations, and predictions in different like the water level. This is really important, water levels, because high water level means like the overflow is likely to have overflow, but low level means like a little bit change of the water level. The top one or the first row is conventional model, the performance of conventional model, and the second row is relevant to the event-based model. You can see here again for the first on the left, first column on the left is related to 1 step. It's more or less like both models are good, but you can see for the high water depth, the conventional models cannot like predict well, but you can see the difference once you're just going to move to like the 8 time step or 12 time steps. The conventional model trying to just move more to the underestimation. And the reason however our model can have like a better performance. The performance, I think it could be like the more or less we can from the hypothesis from the first that we have, because the conventional model work with a large number of like the non-flood events, try to just, it's not very like the towards the like the predictions of the any kind of like the overflow or high flow, and try to just underestimate. And as you can see in the other like the figure, you can see that one as well. And the last figure, sorry, the time. Okay. The last figure I'm just going to show you again. The left-hand side is a conventional. We try to just see the tracking the observation and prediction in 3 types of the rainfall. Rainfall at the top you can see one of them is like a very long rainfall, and the other one is a different intensity, shorts, and the other one is like a high intensity, for example. And the blue lines is the real or the observation. Okay, and the different colors show the different time steps. And you can see here. More or less for like a 1 time step, the performance of the convention is more or less good. But once we have like 8 and 12 time steps, is failed to predict properly. That's the problem here. And again, you can see here, can you see the green one and this kind of like the purple or like a black one? It fails to just predict even the like, you know, this dashed line is the capacity. So it's like exceeding the capacity can predict. So it fails to just predict this one. And the nature of that, as we can see, is because of that. But however, on the right-hand side, our model can just predict for all like different time steps, predict very well. In conclusion, very quickly, I know the time is ticking quickly. And so we have like imputation techniques. So the combination or combined imputation techniques is very efficient to just have like a reliable data. Physically based models are very good for the design purposes and focusing and field focus on real time. But the AI model like the NARX and LSTM, we didn't go through the details. That has been recently, in the recent decade, has been developed a lot, are very good as a first steps, but further progress needs to just be done in the future. Poor performance of the conventional model is due to majority to the non-flood events that we try to just improve that one by trying to just pick up only the event-based like the periods for training. And you can see here the conventional model was unable to predict the overflow for specifically for 8 and 12 time steps, and the accuracy of the overflow detection was quite low or unacceptable. However, the event-based, the accuracy remains high, 53% for 12 time steps and 77% for 4 time steps ahead. And also the event-based model can significantly improve all key performance indicators that we had, specifically for the large lead times or the predictions ahead for between 4 and 12 time steps. For the accuracy and specifically for the accuracy of overflow, it was like between 77 and 53%. And also the computational time, which is really quite important, especially one who's just going to develop any kind of like a real-time model. Okay, so thank you very much. So I mean, this is like the work that we have, like we had like a review work we just published, and this is like mainly like driven from that kind of like the work. Thank you very much for your attention.